Hello friends, hope you are enjoying the Matlab Let's Do Matlab series. This is the second part of matrix application and operation. So we are going to begin up with the operators. The following are listed matrix operators in Matlab. It supports addition, subtraction, multiplication, to the power, transpose, which is conjugated transpose for complex elements, and if we are using apostrophe with the full and if we are using apostrophe with dot, it will be having only transpose whether it's a real or a complex, left division or inverse division or right division. So precedence of these operators are basically, first of all, power is preferred, then right division, after that left division, and then multiplication, after which addition followed by subtraction. Precedence to the parenthesis given at a higher priority. So this is the basic of operators. Let's move to a practical example. First of all, we are going to perform a scalar operation where we will be defining a vector A, and we will perform addition, multiplication, power operations, summation, subtraction, transpose. Then we will be defining a complex matrix or a vector. Will we be performing a conjugate transpose and only transpose operators on that vector or matrix. So let's start. Here I am defining a vector A with value 1, 2, 3, 4. So this is the vector A with 1 into 4 row and column number. I am defining a new variable B, which would be A plus 2. So as you can see, each element is being summed with the value 2. That's why we are calling this operation as a scalar operation. Let's define other variable C, which is equals to A multiplied by B. A multiplied by some constant value 3 plus 2 to the power 2. So as you can see, A's first element is 1, and if you are going to see in the expression of C, I will find that the precedence to parenthesis has been given on the higher priority. After that, the power 2's power 2 is equals to 4, 4 plus 3 equals to 7, and 7 multiplied by A, or the first element of A is 1, it will be giving us 7. So here you can get the idea of parenthesis and the precedence of the operators. Now let's define a new variable D, which is equals A plus B. Here you can also see that the each and every element is being summed up with the other element with the same place value in the matrix A and B. Now E as E equals A multiplied by 3. So here also you are seeing that the each element is being multiplied by the constant value which we had provided in the expression of E. Similarly, let's define a complex matrix H as 1 plus 2z for z semicolon 5 plus 6j 7 plus 8 So here is the matrix. We will perform conjugate transpose operation. We will define a new matrix K and we will be doing transpose operation. Now here you can see that it's a conjugate transpose. It's not a normal transpose, but it's a conjugate transpose. If we are defining the new variable and taking with dot, we will be seeing that it's a transpose, but it's a normal transpose in comparison to what we had seen for without dot apostrophe. Similarly, if we are going to use apostrophe without dot for normal matrix like A, the result will remain unconjugated, or basically there is a no precedence of conjugating. There will be only transpose as a result. So let's do that. So here's few scalar operations what we had learned. This is the test yourself exercise which you can perform on yourself and comment down the answer in the comment section down below. So now we are going to do something more on matrix operators like inverse operation, multiplication, right division and left division. So we had already performed multiplication operation, I think. No, we hadn't performed multiplication operation. So let's perform. We will be multiplying A with matrix B, which are having both are having same order, but let's see whether they are getting multiplied or not. No, why it's not getting multiplied? The inner matrix dimension must agree. As we know, the usually matrix multiplication carries on car rule. Column of first matrix must match to the number of rows of the second matrix. That's why it's not multiplying. Now, if we are trying to do the same but with M, where the number of columns in A is equivalent to number of rows in M, let's see whether it's acting or not. Yeah, it's working. It's working fine. So in a scalar multiplication, we are seeing that the values are getting summed up. Once after it's basically 1 into 5, 1 into 4 column matrix from A and 5 into 1 column matrix of M. That's why we got 1 into 1 column matrix of, or a matrix of order 1 in N with the element 30. Moving forward, we will define a new vector A1 with the values 8, 6, 7, 8, 9, 8, 7, 5, 6. Now to get the inverse of this matrix, we can easily get it with the help of the formula. Sorry, not formula, but actually it's a command. Let's define I inverse as I1, which is equals to I and V of A1. So this is the value of I1. So here right now A1 and I1 is inverse of A1. Now if we are going to perform firstly a multiplication between A1 and B1 or I1, so let's perform a multiplication M1 equals A1 multiplied by I1. By getting an identity matrix, whatever we are getting right now, we can perform the left side division and right side division. So very first we will be performing right side division, where we will be assigning C1 right side division operator B1, which is equivalent to C1 multiplied by inverse of B1. Again, the left side division of B1 left side division operator C1, it is again equivalent to C1 multiplied by inverse of B1. So let's find the inverse of, here B1 is inverse of A1, let's find the inverse of I1 also. So let's a new variable I2 as inverse of I1. It would be the same old vector, and if we are going to multiply this with I2 multiplied with, so here's the inverse M1 multiplied by inverse I2. It will give us the same value as old. Let's perform the old operation. L1 equals, so what we have to do is basically C1 right division operator. So here our C1 is actually M1. So M1 right division operator. Hopefully I'm doing it correct. Yeah. Okay. And I1. See, the result we are getting is same as what we had get earlier. If we are going to do the opposite also, L2 I1 left operator M1, we are again going to get the same result. So what we were seeing that the both values L1 or L2 is equivalent to M1 into I2, where I2 is nothing but actually inverse of I1. Okay, where I1 is inverse of our original matrix A1. So this is matrix operation.